Hello and welcome. My name is Professor Dr. Malik Al-Kasasbe, and I am honored to present this lecture on information retrieval with a focus in Boolean retrieval and inverted index. This is a foundational topic in computer science and data search. Our goal today is to explore how we search for information in large collection of unstructured text. As you can see on the slide, information retrieval is finding material, usually documents, of unstructured nature, usually text, that satisfies an information need from within large collection, usually stored in computers. Let's break this down. Finding material. This material is typically document. Think of article, web pages, reports, or any pieces of recorded information. Unstructured nature. The key here is that this material is usually of an unstructured nature, meaning it's mainly text, unlike structured data in database with clear fields. Text is a free form and disorganized, making it challenging to search efficiently. Satisfies an information need. This is the core purpose of information retrieval. You, as a user, have a question or topic you are interested in, and information retrieval system aim to find the most relevant material to answer that need. Large collection, we are not talking about handful of document in your personal computer. Information retrieval operates within large collection, which are typically stored in computers. Imagine the vastness of the internet or massive digital libraries. Information retrieval helps us navigate this immense data landscape. In a sense, information retrieval is the science of helping users find the information they need from vast unstructured collection of text, most commonly found in digital format. It's what's power search engine and help us make sense of the digital world. So, dear my students, are there any questions so far? Now we will delve into the foundational principle of information retrieval by examining its basic assumption as outlined on this slide. Understanding this assumption is crucial for grasping how information retrieval system operate. In information retrieval, a collection refers to the fixed set of documents that the retrieval system indexes and search. It's the corpus from which relevant documents are retrieved. The size and nature of the collection affect indexing strategies, search performance, and evaluation. For example, the set of all research articles in PubMed or all of pages indexed by Google. Tokenization is the process of splitting text into smaller units called tokens, usually words, term, or symbol that serve as the basic indexing and search unit in information retrieval, often involve removing punctuation and splitting on white space. The token become entries in the system dictionary for indexing. Stemming is the process of reducing words to their root or base form to ensure the different grammatical form of a word are treated as the same term during search and indexing. Helps improve recall in information retrieval matching variation of word. Uses algorithm like Porter steamer or snowball steamer. For example, running, run, man, student, student. The goal is to retrieve document with information that is relevant to the user information and help the user complete a task. In this section of the lecture, we will look at the difference between structured and unstructured data, which is fundamental to understanding information retrieval system. Let's begin with the structured data. Structured data refer to information that is neatly organized into rows and columns, like spreadsheet or relation database. Each row is a record, and each column has a defined data type like number, name, or data. Here's an example from the slide, a table with employee, manager, and salary. We can ask precise questions such as salary less than 60,000 and manager equals Smith. This type of query is direct and logical and works because the structure is predefined and clean. Now, let's compare this with unstructured data. Unstructured data is typically free form text, like documents, web pages, or emails. It does not follow a strict schema or format, make it harder to analyze using traditional database tools. Thus, this is where information retrieval comes in. Information retrieval techniques allow us to process large volumes of unstructured data. The key characteristics for unstructured data: firstly, no fixed table or schema structure. Second, often written in natural language. Third, may include multimedia element alongside text. Fourth, requires specialized information retrieval techniques for searching and ranking. For example, in information retrieval, a search engine that indexes millions of web pages and can return relevant pages for a query like energy policies, even if the exact phrase appears in different contexts. Let's take an example for artificial intelligence unstructured collection, which contain 4 documents. Imagine you are reading this collection and you want to find words that mention artificial and intelligence and not transportation. You could try line by line search, but that would be slow and inaccurate. Information retrieval solve this with smart logic and indexing. In this slide, we will talk about optimizing document search based on term document incidence matrix. Imagine you have a collection of documents, maybe thousands or even millions of articles. Now, if you want to find all documents that contain certain words like artificial and intelligence but not transportation, you could scan through every document one by one. That would be very slow and inefficient, especially as your collection grows. This is where the term document incidence matrix comes in. The term document incidence matrix offers a fast and structured approach to performing complex Boolean search on large text collection, thereby avoiding the inefficiency of scanning documents linearly for every query. A term document incidence matrix is a structured way to index which words appear in which documents. The row represents term words like artificial intelligence, transportation, and another. The column represents document 1, 2, 3, 4. Each cell is 1 if the term appears in that document, otherwise zeros. This slide illustrates the term document incidence matrix for the artificial intelligence unstructured collection described in slide 6, where a value of 1 indicates the presence of a term in a document and 0 indicates its absence. On other way, the column represents document 1, document 2, 3, 4. The row represents every token in the collection without redundant like artificial intelligence, healthcare, education, system, transportation, technology, enhances, benefit, transforms. Each cell is 1 if the token appears in that document, otherwise zeros. To answer a query like artificial and intelligence and not transportation, firstly, we take the vector for each term in query from the term document incidence matrix. Then calculate the bitwise based on query. As you can see, the result revealed that the output for the above query was found in document 1, document 3, and document 4. But there are limitations. Boolean retrieval returns documents that strictly match the query. It does not rank them by relevance. Thus, later we will explain the document ranking. Now imagine scaling up. Suppose we have 1 million documents, each with 1,000 words. That's over 6 gigabytes of text and 500,000 unique terms. Storing all this in binary matrix. Is it practical? The answer is not practical. As we described before, term document incidence matrix would be mostly zeros. We call it sparse. So we need a smarter way to store data. Instead of storing everything, we store only what matters, the document IDs where each word appears. This leads us to the inverted index. An inverted index is a data structure used in information retrieval system like a search engine to quickly find documents that contain given word. It consists mainly of two parts. The first part is dictionary. This is a list or set of all unique terms in the entry document collection. Each entry in the dictionary corresponds to a term. The dictionary acts like a lookup table to quickly find information related to a specific term. For example, the dictionary might contain friend, Roman, countryman. The second part is posting list. Posting list for each term in the dictionary, there is an associated posting list. A posting list is a list of documents where the term appears. Sometimes the posting list also contains additional information like the frequency of the term in each document or the positions where the term occurs. For example, for the term countryman, the posting list might be document 2, document 31, document 54, and document 101. But even with this, we face design challenges. How do we store the index efficiently? How much memory do we need? What's the best structure arrays or linked list? This challenge will be discussed later. The diagram in this slide illustrates the process of inverted index construction, a fundamental concept in information retrieval, which involves several key steps to transform raw document into an efficient search index. The process begins with a collection of documents represented by the example friends, Romans, countrymen. These are the raw text data that need to be prepared for searching. Then the tokenizer component takes the raw documents and breaks them down into individual words. For instance, friends, Roman, countrymen is tokenized into friends, Romans, and countrymen. This stage converts continuous text into discrete unit. The linguistics module receives the token stream from the tokenizer. This stage performs various linguistics processing steps such as teaming or lemmatization to normalize the tokens. This means reducing words to their base or root form. This step aims to group together different forms of the same words, improving search recall. The final output is the inverted index. This data structure maps term to the document where they appear, enabling fast retrieval of documents containing specific query terms instead of searching through document for term. Moreover, the inverted index allows direct lookup of term to final relevant documents. All right, everyone. Let's put what we have learned about Boolean queries into practice. Here's your task. You have this document collection of 4 documents. Your query is lazy and not cat or loudly. You have 5 minutes to work this out in your own or in small groups. Once time up, we will go through it together step by step and see who got it right. Before we warm up, here are the resources for today's lecture. Thank you for your attention, and I would happy to answer any question you may have.